Good morning, students. Dear students, at in the previous video, we had discussed about the numericals based on impulses. Two numericals we had solved on the basis of impulse, and after that, we had discussed about Newton's third law of motion. In Newton's third law of motion, we had discussed about the basic concept regarding Newton's third law of motion, and after that we had discussed about certain implications of Newton's third law of motion. Now, here in front of you, that is part 6 of laws of motion, there is a question, and this question is a very good question. And in this question, there is a mixed concept of Newton's third law of motion as well as impulse. So, here students, first of all, we try to understand this numerical. Here it is given that two identical billiards which you used to play. It is a game that is called as billiard. So, two identical billiard balls strike a rigid wall. This is a rigid wall. I have drawn the figure. This is the rigid wall. And there are two identical balls that strike the rigid wall with the same speed, but at different angles and get refracted without any change in the speed as shown in the figure. There is no any change in the speed. There is no any change in the speed, and the ball is going to the wall, strikes the wall and come back. Here it is striking the ball with an angle of 90 degree or with the angle of 0 degree with the horizontal. With this axis the angle is 0 degree, and with the horizontal bar the angle is 90 degree. In the second case, the ball is going to bend an angle of 30 degree with the horizontal, and it is refracted back by an angle of 30 degree with this line. And while rebounding, while reflecting, the speed of the ball is not going to be changed without changing in speed. Then the first question is, what is the direction of the force on the ball due to the, what is the direction of force? You have to find the direction of the force on the ball due to each ball. This is the first ball and this is the second ball. So first of all we have to calculate for the first ball, that is what is the direction of the force. What is the direction of the force? So before calculating the direction of the force, we have to calculate the rate of change of momentum, that is the impulse, for first case and then for second case. And then in the next question we have to find the ratio of magnitude of impulses imparted to the ball by the ball. In both the cases, first we have to calculate the force, and then we have to find out the impulse imparted to the ball by the ball. What is the amount of impulse imparted to the ball by the ball? So let us solve the question. Dear students, I am rubbing it. Leaving the figure, I am rubbing this of the question for solving it. I think you have understood the question. Now, first we want to calculate, we try to calculate the part first. That is the force, and for the force in figure A, for figure A, the value, that is Px initial. Px initial. Initial momentum for figure A. Initial momentum, suppose I am taking it is as positive, then you can write it as mu. Initial momentum is mu, and the final momentum Px final, that is equal to minus of mu. Since the direction is opposite to this, direction is taken as negative and this direction is taken as positive. So impulse I is equal to Px final minus Px initial, and the value of Px final is minus mu minus P initial, that is minus mu, and it is equal to minus 2 of m. This is the impulse imparted in the first case, and this is the x component of the impulse. This is the x component of, this is the x component of impulse. Now in figure A we will calculate the y component of the impulse. Since the motion is not in y direction, there is no motion of the ball in y direction, so y component of impulse. So y component of impulse I is equal to Py final minus Py initial. Py final minus Py initial. And dear students, here you are seeing that in first case the object is not doing any motion in y direction, it is moving only in the x direction. So it will be the change in momentum in y direction is equal to 0. There is no any change in momentum in y direction. Now we consider for figure B. Now we consider for figure B. This is the first part only, and in figure B. Look at figure B, and in figure B also we will calculate the impulse x component of the impulse. In this case, x component of here we will calculate the x component of. Now look here students, here u is 30 degree, so on resolving it you will get this component as u cos 30 degree, and this component for this velocity for coming velocity, that is u sin 30 degree. Again, for rebounding velocity, you will get the component in this direction, that is u cos 30 degree, because this is going outward, so its component is in outward direction, and this component is outward, this component is u sin 30 degree. So we'll calculate the x component of the impulse, and Px initial momentum, Px initial. Here look at here, This is the initial velocity. So px initial is equal to mu cos 30 mu cos 30 degree, and px final, the momentum, final momentum. This is the initial x component of the initial momentum, and this is the velocity component of velocity, final velocity u just after rebounding. So final velocity px final is equal to mu cos 30 mu cos 30. Now on y-axis, y component of y component, so py initial that is equal to mu sin 30 degree and py final that is minus mu sin 30 minus mu sin 30. Clear, students? This is minus mu. Look at it. Mu in this direction. This is the negative direction. Negative direction of y-axis. This is the negative direction of. So py initial is minus mu sin 30 degree. Py final is minus mu sin 30 degree. Both are negative. Now look at here. P initial mu. This is the negative direction and this is the positive. Any one of you can choose. That is mu cos 30 degree and px final minus mu cos 30 degree. So we had calculated the initial and final momentum in both the cases. Now x component of impulse. X component of impulse. I am going this side. X component of impulse. X component of impulse. You have to calculate the impulse. You know that impulse is the change in momentum, and since you are calculating the x component of the impulse, then px final minus px initial. Px final minus px initial, and the value of px final is minus mu cos 30 degree minus mu cos, this is the final value, this is the initial value, and you can write it as minus 2 mu cos 30 degree, minus 2 mu cos 30 degree. Now we calculate y component of impulse. Y component in this case, 40 seconds. For first case we had already calculated here. Now for second case we are calculating. This is students, this is momentum. X component of momentum. Sorry, we had written it impulse, x component of momentum and y component of moment. Y component of moment. Now, Py final minus Py initial. Py final minus Py initial. And Py final is what? Py final is minus mu sine 30 degree minus mu sine 30 degree and minus mu sine 30 degree plus mu sine 30 degree. It will become what? Minus mu sine 30 degree plus mu sine 30 degree, and its value comes to be 0. So y component of the momentum is 0. Now look here, friends. It is asked in the question what is the direction of the force. So in this case, in second case, the direction. What is the direction of the impulse? Why there is no any direction of impulse in y direction? There is the direction of impulse in x direction. So direction of force is negative side of x-axis. Direction of force is negative direction of x-axis in both cases. Now we have to calculate, because in the previous case also we had got minus 2 mu, the change in momentum, that is minus 2 mu. It is also in the negative direction of x-axis. So both are in the negative direction of x-axis. So force is in the direction of change of momentum. By Newton's second law, you know that force is in the direction of change of momentum. So change in momentum is part B is also negative direction of x-axis, and in case of A is also negative direction of x-axis. So force is along negative direction of x-axis. Now we have to find the ratio of magnitude of, in second part. This is all about the first part. Now for second part, dear students, for second part, we have to find out the ratio of impulse. The ratio of magnitude of impulse, imparted ratio of magnitude imparted to the ball in case of A and B, imparted to the ball in case A and B. So in both the cases we have to calculate the ratio of impulse, and in the first case we had got the minus 2 mu, and in the second case minus 2 mu cos 30 degree, minus 2 mu cos 30 degree. It will cancel out, and the result is 1 upon root 3 by 2, and it is equal to 2 upon root 3, and its value is 1.2. This is done. So dear students, it is a good question and asked in the examination. So we had discussed here. Now we are moving towards the next topic, that is apparent weight of a man in the lift. Apparent weight of the man in a lift. Apparent weight of a man in a lift. Apparent weight of a man in a lift. So, dear students, you all have experienced riding in a lift, and you have seen that when the lift goes upside, lift comes downward. In both the cases, you feel that your weight is certain. With certain amount, you are more weighty, or you had lost your weight. This thing is might be experienced by you all. So here, on the basis of concept of physics, we will discuss here what is the loss of weight when the lift moves upward, when the lift comes downward, and when the lift is moving with acceleration due to gravity g. All these things we will discuss. So let us suppose there is a lift. Let us suppose there is a lift, and in the lift there is a lift, and I supposed there is a lift, and inside the lift there is a weighing machine. Inside the lift there is a weighing machine. Weighing machine. Suppose the weighing machine is placed here, and a man is standing on the weighing machine of mass. A man is standing of mass m. So acceleration due to gravity, the weight is mc. And by Newton's third law, a normal reaction is must, if there is an action, there is equal and opposite reaction. A normal reaction is must be experienced by, and if the lift is moving upward with acceleration p, then what is the reading observed by the weighing machine when the lift is moving upward by the weight? What is the reading recorded by the weighing machine when the lift is moving upward with acceleration a? So R minus mg, the net weight R minus mg is equal to m. This is the total net upward force on the man. This is the net upward force on the, this is the net upward force on the man. And from here we can calculate the apparent weight, the value of apparent weight R. R is equal to ma plus mg. And here we will get ma plus g. The normal reaction R is equal to ma plus g. This is the apparent weight of the man inside apparent weight of the man inside. This is the apparent weight of the man. So what you are seeing, when the lift is a stationary lift is at rest, there is no acceleration of the lift. Then the weighing machine gives the recorded value or records the value only as mg, that is the weight of the man. But when the lift started moving upward, the normal reaction is equal to the normal reaction ma plus g, means in the g a certain value a is being added up. So it is the value of normal reaction, and the man will feel his increased weight. The man will feel his increased weight. So this is the case when the lift is moving. Apparent weight of the man inside the lift, which is increases by his original weight. Now we will discuss the second case. The second case, when the lift is moving in downwards. When the lift is, I think it is clear to all. We have calculated the net force, and from that net force we have discussed about the normal reaction. Now the second case, when the lift is when the lift is moving in downward, when the lift is moving in, suppose here it is g, and g is the weight, Newton's second law. This is weighing machine and this is the weight by Newton's second law. R is the normal reaction, and the lift is moving downward. The lift is moving downward with acceleration e. Now look here, students. As the lift is moving upward, we had calculated the net upward force. For the calculation of net upward force, what we had done? We had done R minus mg, because we had supposed that the net of the upward force is greater than, so we had taken R minus mg is equal to ma. But here we are calculating the net downward force. So we will do what? Mg minus R is equal to ma. It is net downward force. Net downward force on the man. It is the net downward force on the man. So from here we can calculate the value of normal reaction, that is R is equal to mg minus ma, and from here R is equal to mg minus a. R is equal to mg minus a. Now look here, students. From g something is subtracted, means apparent weight is decreased from his original apparent weight is decreased from his original. So this is case second. Now we will discuss case third, in which there is no acceleration of the lift. In case third, if we consider in case third acceleration is equal to 0, if a is equal to 0, and if a is equal to 0, then the apparent weight is equal to the actual weight of the man. Apparent weight is equal to R is equal to R minus mg is equal to 0, or R is equal to mg. Means if acceleration is 0, then apparent weight is equal to actual weight of apparent weight equal to actual weight of the man. This is case 1. Now, if suppose there is a case when the lift, when the lift falls downward with acceleration due to gravity. If the lift falls downward with acceleration due to gravity, means if we are saying that if suppose this is the lift, this is the lift, normal reaction R mg, and if the rope of the lift, suppose lift is hanged by this rope, and if the rope of the lift breaks, then lift starts moving downward with acceleration due to gravity, that is g. And in this case, what will happen? In this case, mg R is equal to mg minus g. That is, normal reaction is 0. And since normal reaction is 0, so no weight of the man is experienced by the weighing machine. Weighing machine. No weight is, and this case is called as the case of weightlessness. This case is called as the weight of weightlessness. This is the case of weightlessness. Dear students, you have seen when you are used to swing on a jhula which is moving like this, and if the jhula goes to its top position and automatically falls down, then you see that you feel that you have lost your whole weight and falling freely. So the same condition will be experienced by the person inside the lift when the lift starts falling downward with acceleration due to gravity. So this is all about today, students. And from in next video, that is tomorrow video, that is part 7, we will discuss one numerical based on this apparent weight, and after that we will discuss about the law of conservation of momentum. So that's all for today, students. Thank you. Have a nice day. Take care.